You are welcome to FANOC Research Group YouTube channel. Please click on the subscribe button to subscribe to our YouTube channel. You will get notified whenever new video is uploaded. Thank you.
We're able to define also partition for a given interval, usually close bounded intervals. So we'll be continuing from there today by giving a proposition. Because if you recall, we made some remark regarding when one increases, that adds a partition, that's a refinement to an existing partition. What happens to the upper the boxsum and what happens to the lower the boxsum? There was some observations we made. So that will now give us the opportunity to define what we mean, or sort of give a generalization of what a partition or a refinement of a partition does to an existing one. So let me give you that proposition and then we proceed. I'm trying to get my tablet so that we can proceed from there. Okay. I think soon be on now. Okay. Yeah, I think you are there now. So, okay, thank you. Okay, proposition. Okay, I think we are there now. So look at this proposition. If I have P to be a partition, of course, a partition are a set of points, x0, x1, x2, and you never can stop at xn, finite points. And also, if you have another partition Q, like this, x0, of course, you can add your refinement in between any of the interval, either between x0 and x1, or between x1 and x2, or between x2 and x3. So the choice is yours. If, for instance, I choose to add it between x0 and x1, that means the additional point, let me call it x star, and then before you now have x1, x1, x2, x3, and so on, and you stop at xn, final set of points. If these are two partitions, of the interval of the interval coming of the interval, two partitions of the interval sorry, let me choose my link again. Okay. Yeah, two partitions of the interval let's have it AB close bounded, where Q contains the Q contains only one point, call it X star. If you check it, Q contains X star more than P. Okay, X star more than P, meaning that Q is a refinement of P, or Q is finer than P. We define all those terminologies if you recall last class. If that is the case, Q being a refinement of P, then we have the following. Then for F, if you define F from A, B close bounded, of course, real valued, of course, this is a bounded function as well. Okay, then we have the following inequalities. We have the following inequalities. The following inequalities. Let me continue from here. We have the following inequalities. Okay. The first inequality is the relationship between the upper the box sum of f with respect to q, as well as that's upper the box sum of the function f with respect to q. Recall that q is a refinement of p. This will be less than or equal to upper the box sum of the same function f with respect to p. In other words, the upper sum diminishes. The upper sum diminishes. The second inequality B is that the lower the box sum of f with respect to q is greater than or equal to the lower the box sum of f with respect to p. In other words, the lower the box sum increases. Lower the box sum of f with respect to q increases, while the upper the box sum decreases. Okay. Of course, we can prove this. We can prove this. Let me share a new slide. Let me share a new slide. Let me share a new slide so we can proceed. Okay. So what we are trying to say is that those are inequal. Let me record those inequalities here. Let me record the inequalities here. The first inequality is that the upper the box sum of f with respect to q is less than or equal to the upper the box sum of f with respect to p. And the second inequality is that the lower the box sum of f with respect to q is greater than or equal to the lower the box sum of f with respect to p. Okay. So of course you can draw a kind of diagram to make sense of how this partition is done. Use your x-axis, this is your y-axis. Okay, if this is your function, for instance, if this is my function and this is my x naught, this is my x naught. Of course, you recall that x naught is descending as a point a, a b close bounded, yxn is b, xn is b. Okay, this x naught, let's assume this is x1, this x2, and so on and so forth, x3, and so on and so forth. Now, if you recall, in between x naught and x star, yes, in between x naught and x1, there is x star for q. So this is x star. I hope you have not forgotten the partitioning. The p P, you have x naught, x1, x2, up to xn. Up to xn. While Q, you have a refinement of P. In between x naught and x1, you have x star, x1, x2, up to xn. Okay, so in between x naught and the x1, you have x star. That's what exactly you have there. So if this is the case, you recall how we normally calculate our um, our upper the box sum and lower the box sum. Now, for here, the lower the box sum, you have the following. Well, let's get interested with that of Q. If you are interested in that of Q, you discover that between x naught and x1, you have x naught and x star, and then x star plus x1. So this x star has partitioned x naught x1 into two. So I will look at the because if you want to compute the L with respect to Q, you need to take care of the MI M1. Let's call it M1 star M1. Yeah, M1 star. Let's call it x M1 star. You have in between x naught and x1. So that would be the infimum. I'm sure you recall what M1 is. M1, do you recall what it is? The small M1. Can somebody remind us what it is?
Yeah, the value of the lower part.
You said?
Just you can take the minimum value in a given interval.
Not just that's not what we call it, not the minimal value. Recall we defined M1 and M2. Okay. So the M1 has to do with the infimum over all the F. Okay. If you take the infimum over all the F, that's your MI. Between here and here, this function, there's the infimum. Okay. I don't want you to say minimum or maximum because the minimum and maximum, as well as supremum and maximum, or minimum and infimum, they are not the same thing. Okay, they are not the same thing. So you must understand that. At least you are. That's why you are doing reanalysis. So there's difference between minimum and infimum. No, they are not the same. In fact, the infimum of a set may exist while the minimum may not. Okay. In fact, the minimum of a set must be in the set. Why the infimum of a set or the supremum of a set may not be in the set. So that's why we are doing reanalysis. So there's difference. So if you have mi star, that would be the infimum over all the f of x, right? All the f of x, such that I don't know if I will redefine it here so that it will be so clear. M1 star will be infimum over all the f of x, such that, in between x naught and x star, such that x naught is less than or equal to x, less than or equal to x star. Okay, so it's in between x naught and x star. Okay, now you also look at between x star and x1. So that we call that M1 star star. Okay, that would be the infimum over all the f of x, such that, of course, x star is less than or equal to x, less than or equal to x1. I'm sure you can see that. You are talking of between x star and x1. So between x1. Okay. Now, if you recall, of course, if you are taking the infimum over x naught and x1. So you recall that M1 is just that this M1 has been broken into M1 star and M1 star star. So M1 will be equal to infimum over all the f of x, right? Over all the f of x between x naught and x1, if you recall that. So between x naught less than or equal to x strictly less than x1. Okay, so with that, what's your observation? You can make the following observation, that M1 star can be greater than or equal to M1. And not only that, you discover that the second one too, which is M1 star star, M1 star star, M1 star star can be greater than or equal to M1. Okay? Because you are talking of M1 star is between here. Okay? The infimum between here and here. While M2 star is infimum between X star and X1. So the infimum. So if you are now talking of the infimum between x0 and x1, this M1 star will be bigger than or equal to M1. While M1 star star, which is between x star and x1, will also be greater than or equal to M1. Okay? So you now discover then that in between x0 and x1, you can now have the following. We can now have the following. We can have the summation of M1 star times the distance between x0 and x1. x0 and x1 is x star minus x0. So that will be x star minus x0. Plus here, the infimum is M1 star star. So you have M1 star star. Okay? Times the distance between x star and x1. What's the distance? That's x1 minus x star, right? X1 minus x star. Okay? So I need to, you now discover that this one will be greater than or equal to M1. Let me go to a new slide and continue that argument. So what we are saying is that the addition of this plus this will be, since this one and this one, both of them is greater than M1. This and this one is greater than, this one is also greater than M1. So the addition of M1 star and plus M1 star star and the distance will also be greater than M1 and the distance between x naught and x1. That's what that argument is saying. But then let's share a new slide and then we'll continue with the arguments. So we are simply saying that M1 star into x1 minus x star minus x naught, x star minus x naught, plus the other one is M1 star star into now x1 minus x star, s1 minus s star. We are saying that this is greater than or equal to M1 into x1 minus s naught. You know. So what's the implication of that? What I have just said is that what this one has to do with, I'm sure you know what this one has to do with. This one has to do with LFQ. Why this one has to do with what? This one has to do with LFP. This is the lower the box sum of the function f with respect to q. the Q partition. The Q partition deals with star. Why this one has to do with the lower the box sum of the function f with partition P. Partition P has nothing to do with star. So that is what you have just shown is that LFQ rather is greater than or equal to LFP. Okay, this verifies the first inequality, one of the inequality that we have shown. Okay, the inequality B. Okay, the inequality B. So you can also similarly show that the upper the box sum of f of q is less than or equal to the upper the box sum of f of p. Of course, how do you do that? The same thing. You know, if you recall, if I draw the diagram here, we have the function there. You have x naught, you have x1, then in between x naught and x1 for partition P, you have x star. So you can now talk of for upper the box sum, you'll be talking of in between here and here, you'll be talking of M1 what? Maybe capital M1 star, which is the supremum over f of x, such that x naught is less than or equal to x, literally less than s star. Then you can also talk about M1, capital M1 star star, which will be the supremum. At the end of the day, you discover that this inequality, just like the way we got the other one, we hold. If you, first of all, you discover that for the supremum, that M1, capital M1 is greater than M1 star. Okay, capital M1 is also greater than or equal to a capital M1 star star. Okay. Okay. So that at the end of the day, the capital M11 star, all of this has to do with this one. So you now discover that this one is greater than this, obviously. So that's why you now have that, obviously, if this is greater than this, it means that this is less than this. So that's how that argument will follow. Okay. Good. So let's what we have been trying to do is kind of tending to defining what we call the Riemann integral. The Riemann integral, one of the most popular integrals in R, in R. Let's look at another proposition. Let's look at another proposition. Another proposition. Proposition. Martin, I hope you are there. I hope you are all hearing me.
Yes, sir.
Are you making sense of the lecture? Or is it becoming complicated?
Actually, last week I got sick and couldn't attend class, so I'm a little behind the schedule.
Okay, you didn't attend the last class.
Yes, so I'm behind the schedule.
Oh my God. Okay, because I want to be sure that let me who again? I want to get some feedback so that I know that we are.
Yeah, for me it's fine.
Oh. Okay, you are fine.
Yeah.
Okay. So what we do as we proceed, Martin, I will continue to re-emphasize on some of the things that we said last class. So I hope you will follow by doing that. Okay. So let f from A to B be R valued, be bounded, Now, if P and Q if P and Q are partitions, if P and Q are partitions of our interval, which is AB closed bounded, and Q is a refinement. Q is a refinement. It's a refinement of the partition P. Okay, then we have the following. You can put all the sums, under the following inequality, that lower the box sum of partition F with respect to P will be less than or equal to lower the box sum of F with respect to Q will be less than or equal to upper the box sum of F with respect to Q, and lastly will be less than or equal to the upper the box sum of F with respect to P. So this inequality holds once you have a refinement of P, by which is Q now. So you have that the lower the box sum of F with respect to P will be less than or equal to lower the box sum of F with respect to Q, and that will be less than or equal to upper the box sum of F with respect to Q, and the largest will be upper the box sum of F with respect to P. Okay? Of course, we've already proved some of these things. We've already proved some of them. But if you want us to look at them again, we can. Okay? Let me share a new slide, and then we come back. Just a few minutes, please. Few minutes. Okay. So we are back now, so we can proceed with the proof if you want. With the proof, we said here that if Q is a partition of P, Q is a partition of P, means that Q properly contains P. Okay, that is, you can define P, for example, as x naught, x1, maybe up to xn. Then you can define Q. Q contains P, means that it must contain at least 1 point more than P. So let's call that 1 point additional, x star, for instance. Then x1 up to xn. Okay, for instance. So with this, you assume that Q has exactly 1 point. Okay, so Q has 1 point and that. So let's, for example, let x star can lie anywhere, either between x naught and s1 or between s1 and s2. The choice is yours. So, but generally speaking, we can say that x1, because it can lie anywhere, we can just allow xi minus 1 less than or equal to x star. Okay, strictly less than xi. This is a general format because a candidate can choose where to put the extra point, either between x0 and x1 in this case. Another candidate may choose x1 and x2 in between. Another candidate may choose even xn minus 1 and xn. So the choice is yours. That's why we are using this. The I, you choose your I where your x star will be. So first of all, recall all our inequalities. I'm sure you remember all our inequalities. Our inequalities is that the LFP is less than or equal to L, F, Q, lower the box sum of F with respect to Q less than or equal to upper the box sum of F with respect to Q. And lastly, less than or equal to the upper the box sum of F with respect to partition P. Okay, so you can do this first or do the anyone there. You can choose that first. So if, for example, I choose to do this first, of course, they are talking of upper the box sum. So you have to get the capital MIs. So I have MI, MI star, MI star, if you recall, what is it? What's the definition? The supremum over what? Or the f of x between xi minus 1 less than or equal to x, strictly less than x star. Okay, I'm sure you remember. You just, you have, for example, xi minus 1. This is the function xi. Okay, this is now your x star. This is now your x star in between xi minus 1 and s. So in between that, you have that. So you also have in between x star and xi, you will now have capital Mi star star, which is the supremum over all the f of x, such that between here, between x star and xi. Okay, so you have x star, x star, x star less than or equal to x, strictly less than xi, which is the last point. Xi rather, xi. Okay, so of course you know that without the partition, you'll be talking of xi minus 1 and xi. So in that case, you'll be talking of mi. This one is capital Mi. This one will be with respect to partition P. Remember, it's the partition P that does not have star. Partition P that does not have a refinement. So you now have that Mi will be the supremum over all the f of x, and straight away, there is no star in between. So you have xi minus 1, less than or equal to x, strictly less than xi. Okay? Than xi. Okay? So what's your conclusion? What do you say about capital Mi star and capital Mi? What do you say? And also, what do you say about capital Mi star star and capital Mi? Huh? What do you say about, clearly you can see that what can you see? You can see that Mi star, capital Mi star is less than or equal to capital. Is it not?
Yes.
Yeah. And also, similarly, capital Mi star star is less than or equal to what? Capital Mi. Is it not?
It's right.
Is it not? So, and of course, you can also see that the distance between xi and xi star is positive. In other words, you see that xi minus 1 is positive, obviously, from xi minus 1 to si. Just like between s1 and s2 is positive, this xi minus si, s minus 1. So, and also the distance between x star, xi minus 1 and x star is positive. Between x star and xi is also positive. Okay? So, if you cannot do all such observation, we proceed as follows. We proceed as follows. Proceed as follows. I want to get a new slide. So what we are saying is that from what we have, Si minus 1, this like S star, this like Xi. So what we are saying is that X between here and here is positive. That is X star minus Xi minus 1 is positive, obviously. You also have between here and here is positive. In other words, Xi minus X star is also positive. Between here and here is positive. That is Xi minus 1 minus X, sorry, Xi minus Xi minus 1, that's between here and here, is positive as well. So if that is the case, you know that here capital Mi has to do with the upper the box sum of F with respect to P, okay, minus the upper the box sum of F with respect to Q, okay, which is equal to the upper the box sum of F with respect to P is simply capital Mi, right, into Xi minus Xi minus 1 minus, you must understand that this one is divided into two between Xi minus 1 and X star. So you take care of that minus Mi. We call the first one as Mi star into X star minus Xi minus 1. X star minus Xi minus 1. Okay. Minus the second part, which is between X star and Xi. Minus, and this second one, we call it Mi star star, right? Star star into Si minus S star. Si minus X star. Okay. Okay. So you discover that this is greater than or equal to this is greater than or equal to Mi into Xi minus Xi minus 1 minus minus Mi into, you know why? Why are we substituting Mi? Because Mi is ab initio bigger than Mi star star. So Mi into X star minus this one now, X star minus Si minus 1. Xi minus 1 minus, substitute this one also with Mi into the distance is the same, Xi minus Xi minus 1. What have you seen? You see that this is equal to 0. This and this, okay, this and this is this. So this is exactly 0. This is exactly 0. This is exactly 0. So what have you done? You have simply shown that this is greater than or equal to 0. That is what you have done is that you have simply shown that UFP minus UFQ, the difference is greater than or equal to 0. If it is greater than or equal to 0, what's the meaning? The meaning is that UFP is greater than or equal to what? UFQ. Is it not? You have justified the last inequality. This is the last inequality now. UFP is greater than or equal to UFQ, or UFQ is less than or equal to UFP. Is it not? That was the last. I'm sure you are looking. You have that theory we are proving. We are trying to prove that inequality, the whole of inequality. What's the inequality? That LFP is less than or equal to LFQ, LFQ less than or equal to UFQ, UFQ less UFQ less than or equal to UFP, 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 UFP. This is the one we just established. This last one, UFQ is less than or equal to, this is it now. UFQ is UFP is greater than or equal to UFQ. It's the same as saying UFQ is less than or equal to UFQ is less than or equal to UFP. I'm sure you can see that. So we've just established this last one. You can also do the same thing to establish this one and then join this and this. The inequality we hold. Okay. So that's all about relationship between LFP, LFQ, UFQ, UFP. Now, we now want to go to the main subject, which is when do we say that a function f is Riemann integrable? That's actually where we are going to. When a function is Riemann integrable. So that will now lead us to the next definition. Hello. Yes. Yeah, I'm in a class. I'm in a class. Yeah. It's okay. It's okay. Yeah. Okay. So we now proceed to have the following definition. Definition. Let f from AB to R be a bounded function, then f is called or is said to be Riemann integrable if you have that if you take all the supremum over partition P of the lower Duboc sum of f with respect to P, and it coincides with all the infimum over all the refinement of P, which is Q now, of all the upper Duboc sum of f with respect to Q. If they are equal, if these two become equal, it means that the function is Riemann integrable. Of course, where P, we know what they are. We already have defined it over and over again. Where P and Q are any partitions. Okay? And we already know what LFP is. That's the lower Duboc sum of the function f with respect to partition P, and the upper Duboc sum of f with respect to partition Q. Q is always a refinement. So this is what when we if this sum is equal to the other sum, then we say that the function is Riemann integrable. Okay, so we proceed by giving an example. Proceed by giving an example. Let's look at this example. let f, let's just take a simple interval 0, 1, and the domain is in R. This function be defined by f of x equal to, is a function that will have two values 0 or 1 depending on what x is. So the value will be 1 if x is rational. X is a rational number. I'm sure you know the numbers that are called rational numbers. And it will be 0 if x is irrational. If x is irrational. Okay, that's how that function is defined. So we want to show, we show that the function defined like this, we show that f is not Riemann integrable. You know, in the sense of what we've just defined, you know, it's not Riemann integrable. Well, if it's not going to be Riemann integrable, that means that that inequality, that equality will not hold. Remember, we said that for Riemann integrability, you have that the supremum over all the LFP must be equal to the infimum over all the, this over all the Q's, while this is over all the P's of UFQs. So that means for this example, this equality will not hold. For us here, what is our solution now? What is our small mi? What's our small mi? Can somebody tell us? And what is our capital Mi? Martin, do you remember? The function is defined, the function will take two values, 0 or 1, depending on what the value of what x is. It will take value 0 if x is irrational. It will take value 1 if x is rational. So what's your small mi? Small mi, you are taking infimum over all the f of x. While capital Mi, you are taking the supremum over all the f of x, right?
Yes.
Is it not the, what we define? Huh?
0 and 1.
What's so small mi is 0 now, while capital Mi is 1, because the infimum over all these, the infimum between 1 and 0 is 0. So the supremum between 1 and 0 is 1. So the small mi is 0, while the capital Mi is 1. Simple as that. So with that, we can now get our LFP. Our LFP, by definition, is simply summation I running from 1 up until n, because it's finite, of all the small mi's into xi minus xi minus 1. Is it not the formula? Huh? The small mi's is 0, right? So
Yes.
you see that you 0 times whatever, when m1 is 0, so you can write it like this, is this will be 0. In fact, this will be 0 because all mi's is 0. 0 times whatever that is here will be 0. Plus when m is 2, m2 is still 0. So 0 times whatever it is 0. When m3 is 0, 0 times whatever it is 0. So 0 plus 0 plus 0 plus 0 is 0. Is it not? Is it not? So I hope you're your UFP, it has to do with the capital Mi now. Capital Mi into if I can share a new slide. Let me share a new slide. But remember, we have already computed LFP. LFP is 0. So the next thing is UFP. Okay, so let's go to another slide now. Okay, so we are here now. We are here now. So we are talking of UFP, U UF UFP. I think the UFP. I mean, the tablet sometimes will be slower. So let's, okay, okay. Okay, that's fine now. So let's see. So what I'm trying to do, okay, okay. Trying to, okay. Try to connect with the tablet. Let's see. Okay. Okay. Maybe I'll go to a new slide to see if that will help us solve our new problem. Let me go to a new slide. Okay, so what we are trying to do is UFP. UFP, I'm sure you recall, is simply the summation I running from 1 to n of all the capital MIs, okay, into the distance between all the successive intervals, which is xi minus 1. We already know what capital MIs are. What are they? What are they?
Which one?
1 now. That's 1. 1 times. When you sum all this, you get the whole partition. Of course, the whole partition is between 0, 1. So if you sum between all the partition, you know, maybe 0 to 0 0.1 to 1, 0 0.1 to all the partition, possible partition you make, when you sum all of them, this is summation. When you sum all of them, the total will be 1. So you now have 1.1, which is 1. So what have you done? You have discovered that you've been able to get 0 when you are talking of the lower the box sum. So this 0 is exactly the same thing as the supremum over all the p's of your lower the box sums of f with respect to p. And you discover that this is not exactly the same thing, is not equal to 1, which you got in this case. 1 is equal to the infimum over all the p's, okay, of u with respect to p. So these, they are not equal. There's, for Riemann integrability, these two will be equal. Of course, 0 and 1, are they equal? They are not, right? 0 is not equal to 1. So this sup over all the LFP is never equal to the inf over all the UFQ. Hence, what's the conclusion? F is not a Riemann integrable. F is not Riemann integrable. So that's that. F is not Riemann integrable. So, okay. So we are still studying functions that are Riemann integrable. So we go ahead to ask a general question. How do we know that a function, even without doing all the computations and all that, because there are some functions that this computation may not be easier to come by, all this computation. So, but generally, there's a theory or a proposition that helps us to characterize functions that are Riemann integrable. That's the next proposition we want to give. A kind of characterization. When a function is Riemann integrable, the following must be satisfied. The following proposition must be satisfied. So let's give it the proposition. Proposition. Okay? A bounded function. A bounded function, of course, defined on a bounded domain, a comma b close bounded, of course, real valued function is Riemann integrable. Is Riemann integrable if and only if for arbitrarily epsilon greater than 0, there exists a partition. Let's call that partition. It's going to depend on this epsilon. So P epsilon, of course, is a partition of your AB close bounded, such that the following inequality will hold, such that 0 will be less than or equal to the upper Dubois sum of F with respect to P epsilon minus the lower Dubois sum of F with respect to P epsilon, and this will be less than epsilon. So what this is telling us is that if F is Riemann integrable, you can always find an epsilon greater than 0, such that if you have a partition, depending on the epsilon you choose, the upper Dubois sum, the difference between the upper Dubois sum and the lower Dubois sum will lie between 0 and epsilon. Okay? The difference between upper Dubois sum of F as well as the lower Dubois sum of F will lie between 0 and epsilon. That's, if that happens, it means that F is Riemann integrable. Okay? And this theory is a necessary and sufficient condition. Necessary in the sense that you see that if F is Riemann integrable, this will hold. And if this inequality holds, it then means that F is Riemann integrable. Okay? So we proceed with more examples. This theory, of course, you can prove can as well be constructed. So anytime I want to show that a function is Riemann integrable, this is what I'll be showing. Yeah, this theory is very important. Anytime I'm asked to show that a function is Riemann integrable, this is inequality. I won't be wasting my time doing all the computations. It's exactly the inequality I want to show. So subsequently, any problem I want to solve to show that a function is, if I establish this inequality, my job is done. That's the essence of this proposition. Instead of showing, I'm sure you recall, the supremum over all the LFQ is equal to the infimum over all the UFQ. You may not easily get all that equality. Okay, but this one you can most of the times you can easily compute it. So instead of going to the definition side, I show this one. I show this inequality holding. Once you establish this inequality hold, it then means that your f is actually Riemann integrable. Okay, so that's the classical result that we use to demonstrate Riemann integrability. Okay, so I'll give another further examples and we'll now continue. Okay. Okay, so I have the following example. Example. The function defined by f of x equal to x squared is integrable. When we say integrable, it's Riemann integrable. Is integrable on this interval on 0, 1 close bound. And as a matter of fact, you can actually do the integration from 0 to 1 of your function. Function is x squared with respect to x will actually be equal to 1/3. Okay, so let's see how we can do this. Let's see how we can do the solution. Of course, choose the following partition. You usually know what we normally do. First of all, we partition the interval 0 to 1. So choose your P, or call it Pn, to be as follows. 0, the first one is 0. I'm sure the last one is 1. You must understand that. So the first one is 0. The second one, call it 1/n, 2/n, 3/n, up to n-1/n, and lastly, the last one is n/n, which is 1. Which is 1. Sorry, this number 1, I hope you know that. So starting with 0 and ending with 1. So that's my partition. So it's just telling you that the distance between each successive, if you look at it, distance from here to here is 1/n. Distance between here and here is 1/n. Distance between this and the next 3/n is 1/n. So you now see that for all the intervals, that the distance between all the intervals, that's xi minus 1 for all the intervals, is simply 1/n. Okay, and that's for all n. That's for all n. Okay, all n, or all I rather, xi for all I. I is counting from 1, 2, 3 up to n. Okay, up to n. Now, in other words, if I share another with this, I want to proceed. Look at the way my P is defined. Look at the way my P is defined. So and also my F is defined as x squared. So knowing P and F, I can now get my small mi, and also get my capital Mi. Okay, I can get my capital Mi. Okay, maybe I share a new slide so that we can proceed. Let me share a new slide. Because if I get my small mi and capital Mi, then we'll now be able to get the lower the box sum with respect to Pn, as well as the upper the box sum with respect to Pn. If we are able to get that, then we'll be able to proceed with the computation of the integral. Okay, so I proceed as follows. I can get my small mi. Small mi is simply the infimum over all the f of x, right? For all the subintervals and all the intervals is I minus 1 over n and I over n, right? Of course, if this will be equal to f of I minus 1 over n, f of I minus 1 over n, which is equal to f is x squared. So yeah, that's simply I minus 1. The infimum over all of this, the infimum is this one now. Infimum is I wouldn't want to say the minimum. Between this and this is the sup, this is the inf, is it not? If you take inf over this, is this one, right? So f of the inf is f of this, but f is x squared. I'm sure you have not forgotten. So that will be I minus 1 over n squared, right? I hope there's no confusion about that. Huh? Martin, do you get that? Martin, do you get that?
Yes, sir.
Okay. The capital MI is the supremum over all the f of x. Of course, you take all the supremum over the same interval, which is I minus 1, I minus 1, I minus 1 over n, comma I over n. Of course, Martin, what is the, between here and here, what is the sup of this set? What is the sup of this set? I minus 1 over n and, this is the sup now, right?
Yes.
This is the sup. So, which is simply f of I over, yeah? So, and f is x squared, you know? So that means this squared. Oh, you said?
I square over n square.
Okay. So, so that's I over n squared. So, with all this now, you can proceed as follows. You can actually find the L of FPN, you know, L of FPN. Remember, the lower, this thing is simply summation mi, right? Small mi into what? Xi minus 1 minus xi. Is it not? That's the formula. I counting from 1 to n. Is it not? But the small mi is already known to us. The small mi is already known to us as I minus 1 over n squared, right? Is it not? I minus 1 over, so which is equal to summation 1 to n of what? I minus 1 over n squared. Now, if you sum all this, the difference between all the successive interval is what? 1 over n. Dot 1 over n. Okay, this is squared though. I hope you know. Dot 1 over n. So if you sum all this, you have I minus 1 over n dot squared, okay, dot 1 over n. You see that what will be common is 1 over 3, because there will be I squared or 1 over n squared, and then there's another 1 over n. So that's 1 over n 3 is common. So you can bring that out, 1 over n 3. Okay? If you do this summation, you have the following: 1 squared plus 2 squared plus so on and so forth up to n minus 1 squared. Okay? That is for LFPN. So I can also do the same thing to get UFPN, upper Duboxon. The upper Duboxon we now do with capital MI. Just like this LFPN did with, dealt with small mi. So let's now compute capital, that's UFPN. Okay, so I proceed as follows. We can actually get UFPN. UFPN, if you recall, is summation I running from 1 to n of capital Mi into Xi minus Xi minus 1. Okay, that's the formula. We already know that. So which is equal to, we know capital Mi. Capital Mi was computed as what? I over n squared, right? If you recall. So that would be I over n squared, right? Times the distances. If you sum all the distance, the difference between all the successive intervals. What's the difference? I hope you have not forgotten Pn. Pn, that's where 0 or comma. What again? What's the have you forgotten? What's your Pn?
1 over n.
1 over n.
2 over n. 2
2
over
over
n.
n.
Up
3
to
over n, right? And so on and so forth. So the difference between each of this now, between here and here, that's 1 over n. That's 1 over n minus 0. That's 1 over n. 2 over n minus 1 over n is 1 over n. So each of them, the difference will be what? 1 over n. Is it not?
yes.
So if you sum this, you see that there's 1 over n squared here. There's 1 over n cubed here, right? So you have, you can bring it out 1 over n cubed into your summation. What will now be left is 1, 1, 1, 1, 1. 1 squared plus 2 squared plus what? 3 squared, and so on up to n squared, right? You said?
Yeah, it's right.
Okay, thank you. So you can now find, I'm sure you recall that proposition that f is Riemann integrable. You need to find, to show that f is Riemann integrable, R integrable. Do you recall that proposition that I said that all I need to do is to show that
yes.
what?
U of fp minus
0 is less than or equal to UFPN minus what? LFPN is less than epsilon, is it not?
Yes.
If I can show that this difference is lying between 0 and epsilon, my job is done. And I've already gotten this. I've already gotten UFPN. I also gotten LFPN, right? I've gotten all that. I've gotten UFPN. If you go to the previous slide, we've also gotten LFPN, is it not? So we can easily do this now and check whether it's lying between 0 and epsilon. That's the next job. Okay?
So it's 1 over n.
Now I go to the. Is that?
The difference is 1 over n.
Okay, yeah, 1 over n could be chosen as epsilon. Okay, so that's already showing you. So it's positive. That's the thing. So 1 over n can as well be chosen as epsilon. So let's now do that now. I think you've already given us the result already. So even with that, you can begin to conclude. Now, if you do this, you now have that given epsilon greater than 0, choose, for example, choose your n to be greater than 1 over epsilon, okay? Then there exists a partition p epsilon, okay, such that 0 is less than or equal to UFP epsilon minus LFP epsilon, okay, and this is less than epsilon. Okay, of course, you discover that all the between successive intervals, that's xi minus 1 is also less than epsilon, and that will happen for all i's. I counts from 1 to n. Okay, now you discover by that proposition, if we label it, that initial proposition, that last proposition, maybe if you call it proposition star, you discover that f is Riemann integrable. So we can now compute the actual integration, and as a matter of fact, you discover that the integral now, which is integrating from 0 to 1 of x squared with respect to x, okay, you now have that, let me share a new slide. You now discover that your LFPN will lie between that integral 0 to 1 of x squared dx. We also lie between UFPN. Okay? You know this candidate, we've already computed it. We also know the other candidate, we've already computed. This candidate, if you recall, is 1 over n3, okay, into what? 1 squared plus 2 squared plus so on and so forth up to n minus 1 squared. Okay, this is less than or equal to this 0 to 1 of x squared dx, less than or equal to this candidate. We've also computed it as 1 over n3 into 1 squared plus 2 squared plus so on and so forth plus n squared. Okay, now this implies that you have that 1 over 3 into n minus 1 all over n into 2n minus 1 over 2n is less than or equal to this integral, which is 0 to 1 of x squared with respect to s. And on this side, this particular one is less than or equal to 1 over 3 into n plus 1 over n into 2n plus 1 over 2n, 2n plus 1 over 2n. So if you take limit as n goes to infinity, what happens? All these terms will go to all these terms as n goes to infinity. You now have that all these terms here will go to 1 actually, including these ones. So that all that you have as n goes to infinity, this integration will go to, this is 1 over 3, this is 1 over 3. 1 over 3 less than or equal to 1 over 3 means that the integral is 1 over 3. Okay? So it then means that the integral as n goes to infinity, the integral of s squared 0 to 1 dx will go to 3, 1 over 3. Okay?
Hello, Prof.
Yes.
Could you go to the previous slide, please? Just let me see something.
The previous slide. Okay. Then the previous slide is this one.
Yes. So,
Yeah.
So does the general formula for 1 over 3 times 1 square plus 2 square plus up to n square is equivalent with 1 over 3 times n minus 1 over n?
Yeah, that's the summation of that's yes.
Okay. What about the upper one? 1 over 3 times n plus 1.
Yeah, 1 over 3. Yes, the summation of, if you recall, the other one, that's on the right for UFPN. UFPN, we had 1 over n3. That's 1 squared plus 2 squared plus this squared. The summation of all of this.
Okay.
Okay, 1 over 3 is still, of course, outside.
Okay. Thank you. Thank
Okay.
you.
Okay, so we want to proceed to basic properties of Riemann integral. Basic properties of Riemann integral. Okay, so that's the next basic properties of Riemann integral. Okay. The first one, I'll put it in form of a theorem. There are 2 of them here, but let's 3 of them rather. The first one says that any constant function, any constant function f from AB revalued defined by f of x, a constant function, it will be just f of x will be a particular number c, where c is a constant. C is a constant. Okay, any constant function of this format is integrable, is Riemann integrable. Is integrable on AB. On AB, and as a matter of fact, the integral from A to B of your function f is c now. F of x is c. So of c dx will be simply the difference between the upper and the lower, which is b minus a times c. That's the evaluation of that integral. Okay, so b minus a times c. Okay, so that is any constant function in R, defined on a closed bounded interval in R, is Riemann integrable. That's first basic property. The second one, is that call it B. Any monotonically non-increasing or non-decreasing function f from AB close bounded to R is integrable. Is integrable on AB close bounded. That's B. The third one is that any continuous function, any continuous function f from AB close bounded to R is integrable. Is integrable on AB close bounded. So those are the properties. Already the first part, which deals with a constant function, we've already solved that. We've already shown that. For example, when I is just 1, you can when f is 1 rather, or f is equal to k, it's easier to show. So let's look at number B. Number B is talking about any monotonically non-increasing. Non-increasing is monotonically decreasing and or monotonically increasing. Okay, so any of them, of course, is integrable. And if you recall, we have already shown some theories regarding monotonically increasing or monotonically decreasing function. Okay, we've already given theories with respect to all of that. Please just give me some a minute, then I will come back and then I'll prove B part. Just a minute. Okay, so we are back, so we can go to a new slide to show that any monotonically non-increasing or non-decreasing function f is integrable, is Riemann integrable. So let's show that. Okay, now if you have if you say that a function is let f be a non-increasing function, non-increasing function on AB. Okay, of course you partition AB, which is your interval, you partition here AB, you get your P as follows. Let P be A is you start with A and end with B. So let A be x0 less than x1 less than x2 less than x3 up to less than xn, and xn of course is B. So let this be our partition. Let this be arbitrarily partition of your interval AB. Now, since f is monotonically non-increasing, what does it mean to say that f is monotonically non-increasing? That is, an plus 1 is less than or equal to an. Is it not?
Yes.
An plus 1 is less than or equal to a. I'm sure we've done monotone sequences now, right? That's monotonically decreasing. Monotonically non-increasing is monotonically decreasing. That's an plus 1 is less than or equal to a. That's that. So since f is monotonically non-increasing, then you can compute your capital Mi and small mi as follows. Capital Mi to be equal to the supremum over all the f of x. Of course, f of x is taking values between all the successive intervals, which is xi minus 1 less than or equal to x, strictly less than xi. Okay? And the supremum of this will simply be what? F of xi minus 1. F of, since, this is monotonically decreasing, an plus 1 is less than or equal to an. So an will be an plus 1 will be less than or equal to an. So meaning that this f of this is bigger than this one. So in other words, you have that this it will be what? F of xi minus 1. F of xi minus 1. Okay? Now for small mi, it will be the infimum over all the f of x, while the f of x will range in all the intervals, which is xi minus 1 less than or equal to x less than xi, all the intervals, Okay? Okay, let me share the next slide. Sorry for that. Let me share the next slide. Okay. So we are simply saying that small mi will be equal to infimum over all the f of xi, and of course all the f of xi is lying between all the intervals, which is xi minus 1 less than or equal to x, strictly less than xi. Okay, you see that this mi will be greater than or equal to f of xi. Okay, so with that, you can now compute your u and l. So UFP will be equal to summation I running from 1 up until n of capital Mi and summation of all the interval, which is xi minus xi si minus 1. Okay, which is Mi is summation from 1 to n of f of xi minus 1. We've already gotten this as f of xi minus 1 dot the interval, all the intervals, which is xi minus 1. Okay. We can also compute your LFP, which is summation I running from 1 to n of small mi into all the intervals, which is xi minus 1. Okay, we've already gotten this as greater than or equal to, so this is greater than or equal to summation I running from 1 to n. We've gotten this as f of xi greater than or equal to f of xi. Okay, and of course all the intervals xi minus 1. Okay, so we can now, don't forget what you are trying to do. We are trying to show that your f so defined is Riemann integrable. And recall that proposition that says, if you find the difference between UFP and LFP and they lie between 0 and epsilon, f is Riemann integrable. Okay, so you can see that theory is very key for us. So now, that will now motivate me to find the difference between this and this. So I am to find the difference between UFP minus LFP. Okay, so I go to the next slide so I can compute the difference and see what it looks like. So I proceed by computing the difference as follows. I have that UFP minus LFP. We've already gotten this, we've also gotten this. So this is less than or equal to summation I running from 1 up until n. For this one, we have got f of xi minus 1. For this one, we've got f of xi, right? Then the difference in the interval is the same for all of them, which is simply xi minus 1. So it's the same for all of them. Of course, the same partition, so it does the same for all of them. So, of course, this will be less than or equal to maximum 1 less than or equal to I less than or equal to n of course the distance is the same, xi minus 1 into this is monotonically non-increasing, so you can be sure that this will be less than or equal to f of x naught minus f of xn, okay, which is exactly the same thing as maximum n ranging from I ranging between 1 and n of course the same xi minus 1 into, of course, this is simply f of a minus this is simply f of b. If you recall, determinants, a is determinant, xn is b determinant, if you recall all that. Okay, of course, f of a minus f of b is greater than 0. Why? Recall, f of a minus f of b is positive. Why?
Because it's decreasing now.
Yeah, monotone non-increasing, that's decreasing. So f of a minus d is positive. Okay, so that is sure. So with that, you can easily conclude. We can have the following, the next 2 or 3 lines we are done. Get the next slide as follows. So since we have made that observation, sorry. Okay. Since f is monotone, decreasing, it follows that f of a minus f of b is positive. So you now have that, therefore, given any epsilon greater than 0, you can actually choose any interval. For instance, choose a partition depending on your epsilon, for which you have that the maximum, of course, I ranging between 1 and n, of all your xi minus 1, okay, times, the f now. You can do for the epsilon all over, since fa minus fb is positive, so I can do the following: 1 plus fa minus fb. fa minus fb. That's what I'm doing. Since this is positive, what I'm saying is that, you have maximum one I ranging between 1 and n of xi minus 1 into epsilon all over 1 plus f of a minus f of b. Okay, this object is positive, so I can do this. If you do this, what have you observed? You simply see that u f p epsilon minus l f p epsilon is less than epsilon. Okay, so that is the job. So I want to, that's today's class for us. I don't know if we have any questions regarding what we have today.
Okay, Prof.
Yes.
I don't understand the last part. I don't know this page. How it could be.
This one?
Yeah. The maximum xi minus xi.
Okay. Okay. If you recall, this is positive.
Yes.
And if this is positive, then, you know, all you need is all of this. If you recall, the other maximum we picked is a number also, and the number is positive. So I can replace such number with this because this epsilon is arbitrarily. So I can replace this, and all this xi is subsumed into all of this. So it's just a matter of choosing something that will help me to arrive at my inequality, which is this one. And what I have chosen is, you know, a summation of all of this. And as a matter of fact, it's also positive. So that helps me to end up my argument. Okay, so that's exactly what.
So instead of f of a minus f of b, just you can replace epsilon naught over 1 plus f of a minus f of b. Small
Yes, this xi minus, when you sum all of them, actually, it will subsumed into the whole of this. It will be subsumed into the whole of this. Yeah. You know, this is a mathematical proof. It's different from example. This is not an example. This is proving a theorem. Okay. So it's not just a particular case. It's not a particular example. So you will not see numbers, you know, unlike those examples we are solving. This is just a mathematical proof. And generally, mathematical proof, all you require is to use, you know, numbers that will not violate your inequality, and your job is done.
Okay, thank you.
Yeah. Okay, so Martin, do you have any question?
No, sir, thank you.
Okay. So with this, we'll be coming to an end. The lectures will be coming to an end here. And